Equations. There's always equations, you know that. Are you doing calculations? Yes, you'll be calculating the lift and the drag around a supersonic body. So what's the purpose of this slide? From level 1, hopefully you've heard about dynamic pressure, which we often refer to as the letter Q. It's a half density times speed squared. Now, in the calculations you'll be doing, there's a representation for Q, which is important, where we put it in terms of the Mach number. You can see it down here. So how do we do it? Q is a half rho U squared, so rho is my density. What I'm going to do here is the same thing. I'm going to introduce gamma, which is the gas constant, specific heat ratio of specific heat coefficients, 1.4. It's always 1.4 throughout the whole of this course. It's only when you get to level 3 and 4 that there are times when it does change. So gamma is always 1.4. And you can see I've put gamma times P on the top and gamma times P on the bottom. Rearrange. We've got a half gamma times P, the pressure. There's a U squared there. And we've got this bracket of density divided by gamma P. This is an important relationship because this is basically the speed of sound, or the inverse of the speed of sound, squared. You can see here. A is the speed of sound. So if I square it, I get gamma P on rho. Or, using equation of state, gamma times R times T temperature, where R is a different gas constant, 285. So if I then substitute for this expression in the bracket, I get half gamma, pressure, U squared on A squared. Well, you know that the Mach number is U, speed, divided by speed of sound. So really what I'm ending up with is a half gamma times pressure, Mach number squared. In the free stream, we often use infinity to define what we mean by free stream. So Q in the free stream is a half gamma, pressure in the free stream times Mach number squared in the free stream. You need that for the calculations, so don't forget it. Okay, we also need to know about total and static. So total tends to be a static quantity plus the dynamic quantity. So we can have static pressure and static temperature. And we can have total pressure and total temperature. So if total is static plus dynamic, total is also the best way of thinking about it is that if you're a molecule and you're heading towards a vehicle, or the vehicle is heading towards you, in our relative sense of running a wind tunnel, we actually have obviously the molecules of air moving and the vehicle stationary. If you were to bring that molecule to a sudden stop, it hits the nose, and basically all its kinetic energy suddenly goes into potential, then it's going to see quite a high temperature rise. That's your total temperature. And basically your total temperature is the same value on a streamline, except obviously the balance between static and dynamic changes, because before we hit it, we've still got a speed. So if you think of total pressure, you run a wind tunnel maybe like the supersonic. We have a big tank, Victorian tank, if you've ever seen it in the outhouse behind it, sort of Victorian, and really does a very good job. But it holds the pressure to force the air through that supersonic tunnel. So therefore we say it's a reservoir, it's not really moving very much. So we would say that was the total pressure and total temperature, the reservoir pressure if you like. So let's have a look at what it means. So in the maths, 0 tends to be total. 1 is a region. It's the region before we encounter the vehicle. Region 2 is after we've encountered the vehicle. So therefore, for our total temperature, we've got Cp. This time the Cp is specific heat coefficient. What other Cp's have we got? Coefficient of pressure and centre of pressure. They're all written slightly differently, but this one is little Cp, specific heat coefficient of constant pressure. Cp times the temperature. For the total, there's no velocity, velocity 0. On the other side, Cp times temperature, this time in region 1, plus the speed the molecules are running at in a dynamic effect, the half U1 squared. If we rearrange, there's actually a relationship for Cp in terms of gamma. And we tend to use this relationship here instead. So it's just the same thing rearranged down there. So when you do calculations, we're looking at ratios from one part of the flow field to another. And wherever there's a shock wave, the relationships are not either side of the shock wave. The relationships you can see here depend on one side, which is the bit, the early bit, before you cross the shock wave. So in any region, this is true. This is the relationship between a static and a total temperature. However, when we cross a shock wave, you'll see a very similar formula, and again, it's just in terms of one Mach number here. What's adiabatic? Well, you've all chosen in the CFD to do adiabatic on the wall. What does that mean? It means that you've specified for your vehicle travelling in your CFD assignment that no matter how fast it goes, there's never a case where the temperature touching that vehicle actually goes into the surface of the vehicle. There's no heat absorbed by the object. So in other words, all the heat is in the flow, and we account for that. Heat in, heat out, heat through the opening, but it doesn't go into the actual solid body. Okay, so therefore adiabatic, we account for it and it's not getting lost. But does not have to be isentropic. So what does isentropic mean? Entropy is really the amount of energy that we've got which we can use for work, in other words, for moving a vehicle. And so if something starts to take away that energy, we say that the entropy changes, usually it goes up, and we can't access that anymore. So for example, allowing heat to go into the vehicle, usually that heat is lost. Heat of a shock wave, normally that is lost to motion. We can't get it back. So in this case, this is interesting because the temperatures, we need to account for the energy, but we can allow a change in entropy. We can allow some dissipative effects, like a shock wave, and that relationship holds. If we then convert into pressure and density, they turn out to be very, very similar, except for the little indice up there. But pressure and density are different. This time, that particular formula only works as long as we have no entropy, if you like, gains. So in other words, we need to conserve the entropy. So that means this wouldn't work across a shock. It only works on one side of the shock or another side of the shock. So that means if we're running something like an engine, temperature's really quite a good thing to actually test total temperature before and after. Is it the same? But if we've got shock waves inside our engine, we know that basically we're going to end up with a loss, as it turns out, in total pressure. And that becomes one of the main ways in propulsion that we evaluate how good the engine actually is.